Hello guys again, and welcome in a new lecture of PCR Primer Designing. So today we are going to talk about how to design a PCR primer. Then I will talk about the main important consideration that should be taken when you design your primer, and after that we will talk about how to calculate the melting temperature, and I will give you a very small example about how to design the primers. And at the end I will talk about PCR primer designing of cloning. So PCR primer designing. It's important to know that the PCR is usually involves three main steps in order to amplify the template of DNA. So that's contain the first step, which is denaturation. The second step, which is the annealing, and the third step, which is the extension. And usually you set the temperature of each step of them. So for example, for your denaturation, you will use 95 Celsius. Some companies provide different kind of DNA polymerase and give you instruction about these temperatures. So some of them saying, for example, 94, it doesn't matter. I've used always 95. And for extension, it's also again the companies that provide the DNA polymerase will tell you the exact temperature that should be used with the kit. So it's normally 70 Celsius, some of them saying 65 Celsius. It doesn't matter. Again, I use always 70 Celsius and 95 Celsius. While the annealing temperature, it depends about the melting temperature of the primer, and this calculated when you design your primer. You will calculate the melting temperature, and then by calculating the melting temperature, this by knowing this value, you will know the annealing temperature, which will be used for the in your instrument of PCR. And this is usually between 50 to 60 Celsius. Okay, so there's some important notice which should be taken into consideration when you design your primer. Typically the primer should be about 80 to 20. So that's the considerations. So the primer length is about 80 to 28 PSPR. It doesn't matter. Some of them saying, for example, 20 to 25. I always use 25 PSPR. However, if you have, for example, a primer for cloning, you will need to add extra PSPR, which is for the restriction sites, and we will talk about that later. So that's the first things. The primer length should be about 80 to 25. I always use 25 PSPR. The typical GC composition, it's about 50 to 60%. So it's high. It's more than the 50 actually, the GC of your primer, and that will give a high specificity. So more G and C, it's mean more hydrogen bonds, and it's mean more specificity of binding in your template. And it's important also to notice that your primer have a balanced distribution of G, C, and AT. So basically, normal distribution of GC and AT. Okay, so that's mean when you design your primer, it's important to avoid the repetitive. So for example, G, 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 and then C, 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 and then AT, for example. So it's important to avoid the repetitive of the G and C, or A or T. However, sometimes, you know, your gene, if you, for example, if you want to clone your gene and you want to start at the beginning from the ATG, the start codon, the sequence after that of the gene is containing a high GC rich, for example, contain a repetitive. Again, it's depend in your in your in your information that you have. So sometime when I design the primer like that, it's normally work well, but it's again, you have to design your primers and you have to set your experiment and see whether there's a PCR product or not. But these are the general information about the features of the good primers and how to design it. Okay, so let's now talking about the melting temperature. So melting temperature actually is the temperature at which half of DNA strands are single and the other halves are double strands. So half of your DNA strands are singles and the other half of your DNA strands are double. So basically, when your DNA template has a higher percentage, so let's say it's higher percentage of GC, it's mean higher melting temperature, and this is due to higher H bond. So this is exactly the definition of the melting temperature. And if you want to calculate your melting temperature, there are different actually equations, and there are also a lot of websites that can calculate the melting temperature for you. So if you have your DNA primer, you can easily just give them the data of your primers, and these websites will easily calculate the melting temperature for you. However, I usually use this equation and it's always work very well. So melting temperature equal to 64.9 plus 41 multiplied by the number of G plus number of C minus 16.4, and that's multiply on the primer length. Yes, so always I use this equation to calculate the melting temperature. And after that, when I calculate the melting temperature, now I can calculate the annealing temperature, which I used to set my PCR machine. So the annealing temperature is equal to melting temperature minus 5 Celsius. That's it. So that's it. It's quite easy. It's just, you know the melting temperature, it's normally 5 degrees less than the melting temperature. However, sometime when you design your primers, you have the melting temperature of forward primer, for example, equal to 67 Celsius, while the melting temperature of your reverse primer is equal to 62 Celsius. So there is a gap between the forward and reverse by about 5 degrees. In this case, what I usually do is taking the lowest melting temperature and then minus this number from 5. So melting temperature of these two primers, the annealing temperature will be equal to 62 minus 5. This will equal to about, it's 57 Celsius. So I usually use this 57 Celsius in my PCR. But I always, when I design the primers, I will try to make the difference is no more than 5 degrees between the forward and the reverse. Okay, so that's about how to take, how to calculate the melting temperature and the main considerations about the primer design. Okay, I think it's important to mention something else before going to designing a primer for a knowing sequence, for example. It's important to notice your primer very well, because there's sometimes something happening which is called, it's forming a structure, it's secondary, what is known as secondary structures. Secondary structures can happen in your primer. So basically, if your primers anneal to themselves or anneal to each other rather than annealing to the DNA template, this can form the secondary structures, and the PCR efficiency will be decreased dramatically, and you will get a very low yield of your PCR product, or there is no any yielding. So basically, there's three main secondary structure can happen. The first one is called hairpin. So the hairpin, if you have, for example, forward primer and reverse primer, and your forward primer start 5 2 3, your reverse primer 5 2 3, what's normally happen, your forward or your reverse, one of them, for example, or both of them, it depends about the distribution of the nucleotide in your primer. So what's happening sometime is, for example, here is in 5, the sixth structure having lead to anneal the primer on itself. So for example, the reverse is fine, but the primer, so forward, is fine to itself. So for example, like that. So if we say, for example, GG, A, and then extra pass pairs, and then for example A again, and then T, C, C, and then again T, A, T, G, etc. And that's why if your 5 end and that's your 3 end. So what's happening is that adenine bind to thymine, guanine, cytosine, guanine, cytosine. Yeah, and this is forming, a hairpin structure. And when this happens, it's to prevent the annealing of your forward primer to your DNA template. Something happening sometime in both of your primers or one of them. And basically, when this happens, that will cause dramatically decrease in your PCR yield. There's also some other structure called self-dimer. So self-dimer mean that the same primer bind to each other. So for example, you have forward here, this forward 5,3. But sometimes these molecules have similar repetitive. So this lead to anneal the forward with itself. or the reverse with itself. So it means there's, you know, a base pair here can bind to each others. So for example, if you have a forward primer with this sequence G, 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 A, T, T, C, C, A, G, G, A, T, C, T, A, T. So that's the 5 end and that's the 3 end. The same primer here will bind to itself. So for example, that's the G, that's the G, and that's the A, that's the A. And then, for example, it's basically, I'm writing this reverse, so it's G, 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 1, 2, 3, 1, 2, 3, and then T, T, and then C, C, and A, G, G, A, T, C, T, A, T. And that's the 3 and that's the 5. It's actually the same primer, so for example this is forward or reverse, and this is also forward, so this forward and that's also forward. What can we see here? That the guanine will bind with the cysteines, adenine, thymine. There's no binding here, adenine, thymine, and again guanine with the cytosine. And in this case, there is a high percentage of similarity, and this leads to bind the molecules of the forward primer to itself instead of binding with others, with the DNA template. So this case called self-dimer. However, there is also sometimes your forward primer, so for example that's 5,3, and your reverse primer is also 5,3. So what's happening in this case? There's a complementary sequence between the forward and reverse, and in this case your forward and reverse will bind to each other. So for example, if we have a forward primer, so that's 5, that's 3 end. So for example, we have G, G, A, C, C, T, T, A, G, G. So that's your forward, that's your reverse, and you have here, for example, a complementary sequence. So here's T, here's G, here's A, probably here T, then G, C, A, T, etc. And that's 3, that's 5, so that's reverse. So what's happening here, there's a complementation, and this complementation need to bind the reverse with the forward. And of course, when there's a binding between forward primer, reverse primer, with ourselves instead of binding with a DNA template, this can lead to prevent the amplification of your DNA, because there's no any primer bind to your DNA template. Okay, so that's a very brief introduction, and then I'm going to talk about how to design a primers for a noun sequence. Okay, so here's the sequence, and we want to design a primer for this sequence. What we are going to take is, so basically when you get the sequence, you will get only the 5 to 3 end. They will not give you the complementary strands. So basically you will calculate from the beginning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 25. So that's 25, that's 1. So from 1 to 25, that's your forward primer. So that's, you will copy that sequence. So that's A, T, G, C, G, C, A, C, 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 T, T, G, A, C, G, A, G, A, T, C, G, G, C, C. Okay, so that's your forward primer. Your reverse primer is slightly tricky to be used. Okay, so you will calculate at the end, from the end, 25 again. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 25. So that's 25 again. And you will write here the reverse. So what you are going to do is taking the complementary strands. So we'll just copy this sequence. So that's G, G, T, C, C, T, G, C, G, C, G, A, C, T, A, C, C, T, G, G, A, C, T, G, A. So that's again 5 to 3. But that's not your reverse. You will take the complementary. So the complementary will be C, C, A, G. So that's 3 and G, A, C, G, C, G, C, T, G, A, T, G, G, A, C, C, T, G, A, C, T. And that's 5 and. And then you will write your reverse primer. So your reverse primer is just starting from here. So that's 5. So these are not your primers. This is not your primers. This is your primers. So your reverse starts from 5 end. So 5. So that's T, C, A, G, T. So I'm talking about the complementary. So I'm just typing it, starting off divided by primer length. Okay, so let's use now this equation. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So GC of reverse 16, and for the forward 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 also. So forward GC will be also 16. So what have named 16? So the melting temperature will be 64.9 plus 41. So that's 16 minus 16.4 divided by 25. And this will be So by using this calculation, so 16 minus 16.4 will be minus 4. This minus 4 multiplied by 41 be 16.4 divided by 25. So that will be 64.9 minus 6.5, and this will be 64.9 minus 0.65. So that will be 64.25. So that will be 64 the melting temperature. So the annealing temperature will be 59, because this is minus 5 Celsius. So that's 59 will be the annealing temperature that we will use it for the to put it in, you know, PCR machine. Okay, so that's the part 1. If we want to use the primer design if we want to design a primer for cloning, it's important actually to know that which type of restriction enzyme that we will add. So basically we'll take the same forward and reverse primer. So that's the forward, that's the reverse, and what we are going to do, so that's the primer starting from 5 to 3, which is, for example, for forward it starts from ATG and end with a CC. And what we are going to do, we will put here the sequence of the restriction enzyme. So for example, BAM H1. And for reverse, for example, if we will use a different restriction enzyme, let's assume that this restriction enzyme will be SAL1, and the reverse is starting from TCAG and ending with again CC. Then we will put the sequence of BAM-H, we will put the sequence of SAL1, for example, or any, you know, desired sequence of your restriction enzyme, and according to the percentage of the guanine cytosine to the adenine thymine, we will use extra 6 nucleotide before the sequence of the restriction enzyme. So if the percentage of GC in your primer is higher than the 80, you will put here 80, 6 nucleotide, or AAAAA, or TTTTT, something like that. But if the percentage of the 80 in your primer is higher than the GC, you will put GC. So remember to add at least 6 base pair before the restriction site, before the sequence of the restriction enzyme. So in this case, the sequence of BAM-H, the sequence of the BAM-H, if you know the sequence of BAM-H, you can just add it actually before the sequence of your primer. Yeah. So that's actually how to design your primers, and how to calculate the annealing temperature. So if you like this lecture, please don't forget to subscribe the channel and give us like. Thank you very much, and see you in other tubes.